Hello everyone, my name is Hanyu Cheng. In Cosmology from Home, I will be presenting our latest work conducted in collaboration with Professor Luca Vicinelli on future targets for light gauge bosons from cosmic string. I will start with an introduction to cosmic string. Next, I will discuss the gravitational wave emission from cosmic string and explore the analytical behavior of gravitational wave spectrum. I will also discuss the role of gauge boson in this process. Finally, I will show the target constraint for the model. We know that throughout the universe's thermal history, several symmetry breaking phase transitions may have occurred, leading to the formation of different topological defects like cosmic string. As shown in this figure, in the early universe, after symmetry is breaking, the fragments in different horizons can have different phases. As the universe expands, when these horizons meet each other, due to the continuity of the field in space and time, there must be a place where the phi field value is zero, corresponding to the maximum potential energy. This is the principle of the generation of topological defects. In our work, we employ the abelian Higgs model for cosmic string. Phi is a complex scalar field, and A is a gauge field in dark sector. The U1 gauge symmetry is broken at the gauge scale V. We treat MA and V as two independent quantities in our work. Next, we turn to part 2. We know that the equation of motion in abelian Higgs model allows a solution for cosmic strings, characterized by their tension mu. This string can intersect and form closed loops, emitting gravitational waves during relativistic oscillation. This is the diagram of string network based on other simulation results and the diagram of loops emitting gravitational waves through oscillation. First, we discuss the only gravitational wave case. The angular rate of the loop is dependent on string tension mu, and the formation time of loop is dependent on string tension mu, frequency f, and the emission time t. By analyzing the loop formation and decay through gravitational wave emission, we can determine the gravitational wave density, omega GW, seen today. Next, we consider a case that loops both emit gravitational wave and gauge boson. Since the energy of the standing wave on the loop is inversely proportional to the length of the loop, loops with a length less than 1 over ma prime, which you can see here, that is loop formed before the critical time Ta prime, which you can see here, can emit gauge bosons. Taking these effects into account, the string tension mu, the formation time Ti, and the gravitational wave energy density are modified to depend on ma prime as well, which you can see from this equation. By calculating the lifetime of the loops in both cases, we find that the lifetime of the loop emitting only gravitational wave is inversely proportional to g mu, which you can see here, which is much longer than the lifetime of the loops emitting both gravitational wave and gauge bosons. indicating that the emission of massive gauge boson is the dominant channel of energy loss before critical time Ta prime. This means the gravitational wave emission is suppressed dramatically for loops formed before critical time Ta prime. Next, we turn to part 3. In this part, I will discuss the analytical behavior of gravitational wave spectrum. We still first consider only gravitational wave emission case. As you can see here, we divide the contribution of gravitational wave spectrum into 3 terms. The first term is the roots formation during RD and the gravitational wave emission during RD. The second term is the roots formation during RD and the gravitational wave emission during MD. The third term is the roots formation during MD and the gravitational wave emission during MD. We also model the scale factor for RD and MD separately. Then we can write down the detailed formula of gravitational wave energy density and the formation time Ti for 3 terms separately. The following shows the analytical behavior of the gravitational wave spectrum from 3 terms at low and high frequency. For the first term, for the first term, omega GW from RDRD is a propotential to F2 3/2 at low frequency and does not depend on F at high frequency, only depend on string tension. We define the pivot frequency F star as when F larger than F star, omega GW is propotential to F2 minus 1/3. Therefore, omega GW from RDRD does not have a pivot frequency in this case. This fits very well with the red dashed line in the figure of numerical results as you can see here. For the second term, omega GW from RDMD is a propotential to F2 3/2 at low frequency. It should be noted that when F smaller than 10 to minus 11 kHz, K is mode. In order to ensure Ti smaller than T equal, the upper limit of the integration must be less than T0, resulting in the omega GW being propotential to F2 5/2, as you can see here. At high frequency for few modes, omega GW is propotential to F2 minus 1. For summation of large modes, omega GW is propotential to F2 minus 1/3. The pivot frequency is inversely propotential to gamma GW G mu T naught. This fits very well with the red dotted line in the figure of numerical results, as you can see here. For the third term, omega GW from MD is propotential to F at low frequency. At high frequency, for summation of modes, omega GW is also propotential to F2 minus 1/3. The pivot frequency is also inverse propotential to gamma GW G mu T naught, and the value is smaller than that of RDMD. This fits very well with the blue dashed line in the figure of numerical results, as you can see here. In the parameter space we consider, the minimum value of MA prime is 10 to minus 15 electron volts, and the corresponding critical time is much smaller than T equal. Therefore, only the loops formed during RD would be affected. Since the gravitational wave emission from loop formed before the critical time Ta prime is dramatically suppressed, we analytically approximate that the contribution of this loop to gravitational wave spectrum is zero. Therefore, for integration, we only need to consider the contribution of loops formed after critical time Ta prime. Taking this into account, we change the lower limits of the integration time in the RD-RD term and the RD-MD terms to Ts. As you can see here, the MD-MD term would not change. Therefore, including gauge boson emission will lead to the high frequency contribution of omega GW from RD-RD to be suppressed. From a flat curve to potential to F2 minus one third for summation of modes, as you can see here. Then we derive the pivot frequency F star for RDRD, which depends on MA prime and string tension mu. We also obtain a more general expression for pivot frequency of the RDMD, which also depends on MA prime and the string tension mu. These results are in very good agreements with the numerical results. As shown in this figure, the dotted line in the figure is the result of total modes equal 15. And the solid line is a semi-analytical result corresponding to numerical results that total modes are very large. Based on the analytical results we obtain, we can semi-analytically plot the gravitational wave spectrum of cosmic string, avoiding long time of numerical calculation and underlying errors. In the final part, I will discuss the target constraint for the model. As we have seen, the pivot frequency depends only on MA prime and mu. The string tension mu only depends on the energy scale V. So the pivot frequency only depends on the MA prime and V. Actually, in our model, the shape of gravitational wave spectrum is dependent on the gauge boson mass MA prime and energy scale V, as shown in the figure. A set of MA prime and V value determines a spectrum. As you can see, these three different colors line. Since the spectrum spans a wide range of frequency, we can use ground-based interferometer and space-based interferometer to constrain the model parameter at the same time. Finally, I want to show a figure of constraint on the model parameter MA prime and V. We consider a range of gauge boson mass, which is 10 to minus 15 electron volt to 10 to 3 electron volt. And the range of energy scale V is 10 to 7 giga electron volts to 10 to 15 giga electron volts. Since the smaller the gauge boson mass, the more severe the separation at high frequency. The bond of ground-based interferometer interferometry wakes up at low mass, as shown by green, blue, and pink curve, as you can see here. Since the pivot frequency f star is always larger than the range of space-based interferometer, the bond of space-based interferometers is not affected by gauge boson mass, and should be theoretically be the same as a global string bond, as shown by the purple, red, and this yellow curve. Since BBO has the highest sensitivity, it gives the strongest constraint. As you can see, this yellow curve shows BBO will be able to extend the search for cosmic string to way smaller than 10 to 8 giga electron volt. Besides, color and shaded areas shows the nanograph hints string tension in the range as Gmu larger than 10 to minus 11 and smaller than 10 to minus 9.5. And red shaded area shows the black hole superradiance bond. And the gray shaded areas shows the dark matter abundance bond, as you can see. Due to the time limitation, I will not give the summary again. Thanks for your listening.